Hey guys, this is Jim, WT1W, and you're watching FEPLabs Radio. Thanks for stopping by. Appreciate it. So today I want to share with you a device I bought at the ARRL auction. That's hard to say. ARRL auction. That was like about a month ago, and they had a number of items that were donated for them to auction off. Some of it was donations from hams like us. Some of it was stuff they had purchased and they were using in their lab. So there was quite a price range of gear and quite a wide range of gear. And so as I'm perusing this for things I don't need but I could save money on, I came across a step attenuator. So this is an old device, and I'm guessing somewhere in the 60s, 70s possibly on this thing. I haven't been able to find a whole lot of information about when this was designed, but it appears to work, and we're going to take a look at it today. So let's jump in and take a look at what a new current step attenuator looks like. Okay, so I pulled up, this is on DigiKey, and a number of places sell these things. And this particular one here looks like it has steps 20 dB, 10 dB, 8, 4, 2, 1.5 a dB. And the way these work is you can just press the 1 and have 1 dB of attenuation. You can press 1 and 2, and then that'll give you 3 dB of attenuation, and so on and so forth. So if I math this right, that would be 20, 30, 8 plus 4 is 42, plus 3 more is going to be 45.5 dB of attenuation for this guy. And these things will have a range, HF, UHF, VHF, so on and so forth. They also will have a power input amount that they can tolerate. So we're going to take a look at the one I have up close, but I wanted to show you what a new one looks like. Now, if I get rid of this picture, we can see here on the DigiKey website, they've got this guy for sale. And this is a 0 to 45.5 dB attenuator, 0 hertz to 750 megahertz, 50 ohms, a 1 watt BNC inline module. So it is limited on the amount of power that it can take in. And if we look at the price over here, wow, $1,300. Now this is Pasternak, so this is obviously some high dollar precision equipment. That's what a current one looks like, around what a current one costs. Let's take a look at the one I have and talk about it, and then we'll look at the innards, and then we'll hook it up to the spectrum analyzer and see if it does the thing. Okay, so here is the attenuator, and you can see here that we have different buttons that give us attenuation in different increments. These are 20 dB a piece, 10, 10, 10, 4, 3, 2, and 1. So if we add these all up, 60, 70, 80, 90, 94, 97, 99, hundo. So this will do 100 dB of attenuation. Now, I haven't been able to find the exact specs on this yet. I found a couple of photocopies of dusty magazine articles from the early 70s, late 60s. They didn't really say what the input power range was on this. I've got this from the auction for 40 bucks plus shipping, maybe 45 plus shipping. So I'm not into this for a tremendous amount of money, but before I jam 100 watts into it, I want to see what this thing is rated for. It does say on the front here, you can kind of see this. This is the model number, and I can't really see a range. It's not marked. On the frequency range, it is a 50 ohm impedance on this. And I'm guessing that the Davin company is out of business or has been bought out 3 times since this was manufactured. But this thing is built like a tank. This thing weighs about 5 pounds. It is not lightweight. We have the 2 BNC connectors here. There's nothing on the back or the sides. Now, I have taken the liberty of removing some screws already, so we don't have to waste time doing that on camera. So let's take a look at our innards here. This is the front cover of our attenuator here. And if we look at it on the back, you see we have these two, I'm going to call them modules, that are wired in series together, and then they're going to be wired in series inside because we're adding in, or parallel because we're adding in resistance. So that's what it looks like on the innards. Now, because I love doing this kind of stuff, I already took this lid off. And they don't want this lid to come off. They really don't. This is the lid that goes right there. And there are a lot of screws, and they're very small flathead screws. And so we can see inside here, but you can see in here, each section is shielded from the other. So there's attenuation there. And we also have then all of our components in the network. We have a large resistor, and these are all slightly different values. And then we have some, what I believe are precision resistors also in this network. Now, in my understanding of an attenuator, there's not going to be any other component short of switches, wires, and some solder. This is all basically resistance. So that's what the innards look like. Each end is connected with this fancy little connector here. I think that's more just of a bushing for the cable. I didn't take all that off because I don't want to actually break this thing accidentally. So that's what the insides look like. I'm going to assume that the other side is pretty much the same kind of deal. And now let me put this thing back together, and we're going to hook it up to the Siglent SVA 1015X and take a look at what it looks like on a Spectrum. I have got the Siglent SVA 1015X hooked up to the attenuator box, and I have the tracking generator enabled. Now, there is not enough room on my desk, nor have I got the right camera set up to show the actual things, but they're sitting right down here. So what we're going to do is I'm going to start rolling in attenuation, and what you'll see is one of the markers will stay flat, that is our reference line, and the second marker will drop down and show you what attenuation we're rolling in. Now currently, at this moment, we are on 1.8 to 30 megahertz. This device, from what I can tell, goes up to 225 megahertz is the frequency range specified for it. I played with this a little bit, and I don't think we're going to attenuate much above 30 megahertz, but we're going to take a look at 1 to 30 first. And what the heck, we'll go to the full range of the spectrum analyzer and go all the way up to 1.5 gigahertz. So as you can see on the screen here, we are, make sure I'm looking at the right screen, we are set for a start of 1.8 and a stop of 30 megahertz. So that is our entire range. Now, as I roll in attenuation here, you can see we drop down, and if you look up here in the corner, you'll see we're getting 1.8 attenuation, the delta difference. The marker 2 delta 1 is our reference line, and then M1 is our actual attenuation, and of course the frequency that we're on. And you can see here across the frequency band that it's pretty much static where we are. Now let me change to the marker screen, and we can look at the marker here, and you can see that it's pretty static across that whole range. That green 2 delta 1 marker is what our attenuation is going to be. So that's 1 dB of attenuation according to the box. Let's turn that off. And you can see we go back up. And so we've got about 0.8 dB of attenuation on this setup. Now, when I set this up, I did zero it out with the tracking or the attenuator in the middle with no attenuation. So that is our reference line. The tracking generator is putting out a 0 dBm signal. So we've already got 0.8 just from being connected to this attenuator. All right, so here's 2, and you can see we've dropped down. The blocks are set to 10 dBm per block. I could set it smaller and we could see it drop more lines, but then it's going to go off scale pretty fast. So that's doing what it's supposed to do. 2.7, and with our 0.8 magic attenuation loss from hooking up this device. That's 2 dB of attenuation beyond what it originally was. So let me turn that one off. Actually, let's turn on the one. We drop down to 3.8. Let me cut those off. There's number 3. I think it's 3. Yep, that's 3. And we got 3.8 to 3.9 attenuation. And then we go to 4. And there's 4.8. Again, that extra 0.8 is our loss, our insertion loss from plugging this in line on the spectrum analyzer from the tracking generator where the signal starts to the RF input where we're actually measuring the device under test here. So just ignore the 0.8, that comes with it. I could actually go in, I think, adjust and filter that out with the spectrum analyzer, but I'm not going to worry about that for this. So as you can see, as I hit each button, there's 10.911 dBm on that button, and then those are also 10s. There's 20 right there, and that gives us 21 dBm of attenuation, which is what I'd expect. And all 3 of the rest of the buttons are 20, so if I hit 2 20s here, for example, then we get, and if you look again up here in this upper corner right there, you've got 41 dB of attenuation. So the way these things work, this is all adds together, right? So I've got 2 20s pressed right now. If I knock a 10 down, then you're going to see that we drop down to 50 dB of attenuation. And if I knock down the 1, the 2, and the 3, that gives us 50, is that right? 1, 2, and 3. So that's 6 more dBm of attenuation. And as you can see, it's not exactly staying steady, but there you go. It does work like that. So let me back these out. And let's just set this on 10 right there. And then let's change our frequency range and see what this looks like across a wider frequency range. So what I'm going to do is change the stop frequency and start dialing range on it up. And as you can see, our marker's moving to the left because I'm dialing up the stop frequency, which is this number right over here on the right side. Right there, marked in blue. So we're up to 56. And let's take out our 10 dB. And this is really what I wanted to show you. So as that frequency goes up, our insertion loss on this device is actually increasing. So we are down right here. We're down 3 dB right there. And that's with nothing enabled on the attenuator. So that's what I was saying is these are somewhat frequency dependent. Let's go back to our frequency range and start rolling up our stop frequency a little higher. And as you can see, it gets pretty sketch as we go farther and farther. So now we're up past 2 meters. Back it up a little bit. And then let's go take a look at our marker. And you can see here, we are down minus 16 dB. And our reference line has also dropped to minus 1.21 dB. The tracking generator is putting out a 0 dBm signal. So while this says it may go to 225 megahertz, it's not exactly flat across that entire frequency. So let's jump. We're on, well, actually, we're up past it. We're up to 245 right now. So let's go change that frequency and go to 225. Oops, I don't want to do that. Back up. Stop. 225 megahertz. So there is our entire official range of this attenuator box, and you can see we still have the dip there, and that dip is at 83 megahertz where we lose 16 dB of signal. So obviously this thing is old. It is not new. It seems to look pretty legitimate across the HF bands, but once you get above 35 or 50 megahertz, as you can see back there on marker 1, then we're not exactly staying flat. And if at 83 megahertz, which is what is right here on the screen at this moment, where that number 2 marker is, that's minus 16 dBm. But then if we move that marker up, that was me touching a cable. Interesting. That's really strange. I literally just touched this with my elbow. So yeah, there's probably loose or old connectors in there. Yeah. I'm just barely touching the BNC input connector. So it's a little sensitive. Let's go all the way up and let's go to our span and let's just zoom this thing out all the way and go to our full span. And you can see, so now that is from 0 to 1.5 gigahertz. And you can see it's pretty squirrely when it gets up that high. So, you know, this is great for HF. If we go back and change our stop frequency, we'll start at 1 megahertz and we will stop at 30 megahertz. And you can see we have a straight up attenuator with 1.09 dB of loss at this point. These are old components. You know, it could be heating up a little bit. I mean, we're not putting out much of a signal. 0 dBm is 1 milliwatt, I believe, is 0 dBm. But it does the attenuation thing. There's 20, there's 40, 41, 42, 43. So pretty cool. Anyway, what would we use this for? Stuff on the HF. If you, I mean, right now, the way it is, it would work. You'd have to put it in line with a receive-only antenna. So it would work well with an SDR. I would not transmit 100 watts through this, not even close. What little I've seen on documentation on this is it's not really rated for more than a few watts. 2 to 5 watts total. So you couldn't really hook this up to an HF radio that you're going to transmit through. You'd have to take this out of circuit while you were transmitting. You could use it to attenuate a very strong input signal. For something like a scanner, absolutely you could put this in line. Now, a lot of scanners have a minus 10 dB attenuator switch on the back of them. That's very common on a lot of scanners, just to knock down super loud, strong signals. You could also use this with an SDR. So you could start tweaking out some of the noise by dropping the attenuation down if you were trying to listen to a strong signal and had a bunch of background noise. In any case, that's what it is. That's what it does. Guys, I hope you got something out of this. If you would, give me a thumbs up. Make sure you're subscribed to the channel, please. It's in the dingus below. There's also a little bell down yonder that you can click, and you will be notified of whenever I post any new videos. Y'all, thanks for watching. Have a great day. 73.